The ideal gas law. So our goal today is to learn about the ideal gas law. So here's a quick video to give you a review of the combined gas law.
We filled this barrel with a couple inches of water, and we heated it up so, as you can see, it's like turning into steam. And then we're gonna quickly put this can filled with steam into the bucket of ice water, and it should crush. That's because it's going to go through a rapid phase change where the steam is going to condense quickly into water vapor, and pressure inside of the can is going to be less than the pressure from the outside, and it should crush. It should implode. Thank you!
Tight. Twist. Twist.
That's hot. You want to do it? I don't want to do it.
That's fine. Squeeze.
Should I sign something?
Insurance.
I want a single. Come on, go!
Patience, patience, my child, patience.
No, you can't hit it.
Oh no, my God, the stopper is getting pulled in.
Yeah, I'm looking a little bit.
Does that mean it didn't work?
Now, throw some water on it. Yeah. Oh no, just grab the ice, Yoon, with your hands. That is so wimpy.
Well, I'm scared that it's gonna blow up in my hands.
Wait, look.
Oh,
Mr.
Abrams, do it.
I think
Yeah.
it's getting concave.
Oh, yeah.
So in this video, you saw the can completely crush. And what happens here is that as it cools down, some of the gas, the water vapor, becomes liquid, which means you reduce the number of moles. And also the temperature is going down, which means that would mean you'd reduce the volume. The number of moles reducing means you would reduce the volume eventually. But what happens is the pressure goes down. The pressure goes down in the can, and eventually the atmospheric pressure overcomes that and gives you your new final volume because the pressure overcomes the strength of that barrel. So the ideal gas law, PV equals nRT. So this is pressure is in atmospheres, volume is in volume in liters. Pressure can actually be in other pressures, but it changes the value of R. N is number of moles, and R is the proportionality constant, which is 0.08206 liter atmospheres per mole Kelvin. This is if the pressure is in atmosphere. If you change the pressure and you put it in other units, it changes the value of R. But for the most part, we're going to be using 0.08206. So the temperature is in Kelvin. So an ideal gas is something that behaves ideally. It follows all of the postulates of kinetic molecular theory. Now, there are no ideal gases. There's no such thing as an ideal gas. They're imaginary gases that perfectly fit all of the assumptions of the kinetic molecular theory. That gases consist of tiny particles that are far apart relative to their size. That collisions between gas particles and between particles and the walls of the container are elastic collisions, and that no kinetic energy is lost in elastic collisions. So, gas particles are in constant rapid motion. They therefore possess kinetic energy, the energy of motion, and there are no forces of attraction between those gas particles. And the average kinetic energy of gas particles depends on temperature, not on the identity of the particle. Real gases, they don't behave ideally. However, they do experience intermolecular attraction, so they don't behave ideally. They do have volume. They do not have elastic collisions. They're actually slightly inelastic. But real gases will behave ideally when they're at high temperature and low pressure. They have lots of space between them, and they're small nonpolar gas molecules. They're not likely to interact with one another. So real gases are likely not to behave ideally at low temperature and high pressure. So once you start putting them close to one another, and you start to see the effects of their intermolecular attractions and their volumes. So large polar gas molecules, so things that have a lot of volume and a lot of intermolecular forces.